Everyone, welcome to our second lecture on gravitation. And in this lecture, we will discuss about Kepler's laws of planetary motion. And before coming to Kepler's laws, we have to understand what is ellipse. So, ellipse is basically stretched or skewed form of a circle. If you stretch a circle, if you stretch a circle like this, you will get an ellipse. This is horizontal ellipse, and if you skew the circle like this, then you will get vertical ellipse. So what is the difference between a circle and ellipse? uh, if you see a circle, you can take any point on the surface of a circle, and if you try to find its distance from the center of a circle, it will come same for all the points, and this length we call radius. So if you can take any point on the boundary of circle, and its distance from center of circle will be same, and this is radius. But in case of ellipse, how we define a ellipse? Take any two fixed point, and we are taking two fixed point, f1, this is focus 1, and this is focus 2. Combinedly we say foci. Foci is basically plural of focus. So you can take any point on the curve of the ellipse and try to find its distance, sum of its distance from two fixed points, uh, focus 1 and focus 2. That sum of these two distances will always come same. In circle, distance of point from center comes same for all the points, but in case of ellipse, sum of these two distances means sum of distance from focus 1 and sum of distance from focus 2 always come constant for all the points on the curve of the ellipse. Like if some this is point A, and I am taking this point B, and for point A, if this length plus this length is 10 centimeter, L1 plus L2 is 10 centimeter, then if you join B, point B with F1 and point B with F2, this one will be L1 and this one will be L2. In this case also, L1 plus L2 will come 10 centimeter. You can take any point. You can take point C here, any point here or here. Sum of distances from F1 and F2 of any fixed point will come same for a ellipse. This is how we define a ellipse. Ellipse is basically a geometrical figure, and for circle, any fixed point on the boundary of circle is at same distance from the center. But in case of ellipse, any point on the curve of ellipse, it is at like distance of its distance from focus 1 plus its distance from focus 2 will come same. This is ellipse. Now how can we draw a ellipse? Fix two iron nails. Here I told you that L1 plus L2 for any ellipse is for any point on ellipse is constant, and if you take two nails and tie a thread with these two nails, and length of that thread must be greater than the distance between these two nails. Suppose this distance is d, so length of your thread must be greater than this d, and stretch this thread completely. Like take this thread in upside direction, maximum you can so suppose this is maximum distance. At maximum distance it becomes, suppose this is maximum distance, so at maximum distance it becomes like a triangle. And put a pen here and try to rotate it or move it in all direction. Try to move this thread in all direction with the help of a pen. Then you will get a ellipse. You will get the shape of ellipse. I will explain this thing in a short video. I will show you how to draw this. So this part is clear. Now we will see some more things about ellipse. As I told you that focus ellipse has two focus points, f1 and f2. If you draw a line passing through f1 and f2, you will get this line is called major axis, and in between these 2 points f1 and f2, exactly between these 2 points, means if this distance is d, then this distance should also d, and if you pass this point which is in exactly in between f1 and f2, this point is called center of the ellipse. If you pass a line vertically through this ellipse, this you will get minor axis. So this is major axis and this one is minor axis. Major axis will be bigger in length and minor axis will be smaller in length, and this whole line is major axis. If you take half of this, means this total distance is major axis, but if you take from center to this point, you will get semi major axis. Semi major axis. I will tell you use of this semi major axis in upcoming section. So this part is clear. I am going to erase this part. Now coming to Kepler's laws. In ancient time, people used to believe that planets orbits, planet revolves around the sun in circular path. Ancient Greeks, and at that time, all the people used to believe this thing. But Tycho Brahe, scientist, uh, wants to confirm this that planets revolve around the sun in circular path. So he started taking data of the motion of planets around the sun, and he collected data for many years. But after his death, his assistant was Kepler. Kepler was the assistant of Tycho Brahe. After the death of Tycho Brahe, Kepler used the data taken by the Tycho Brahe, and that data was um, motion of planets around the sun. And first, Kepler try to fix that data in the equation of circle, but uh, that data was not matching with the equation of circle. Then Kepler tried other geometrical shapes, and then he found that this data is in agreement with equation of ellipse. Data of orbits of planets was in agreement with equation of ellipse. Then he concluded that planets orbits around the sun in elliptical path, and this is also the first law of Kepler. From the data taken by Tycho Brahe, Kepler confirmed that planets revolve around the sun in elliptical path. Now coming to Kepler's first law. Kepler's first law is planets revolve around the sun in elliptical path. Elliptical path with sun is situated at one of the two foci. One of the two foci. As we discussed earlier, ellipse has two focus points and combinedly called foci. So, according to Kepler's first law, planets revolves around the sun in elliptical path with sun is situated at one of the two foci. This is F1, this is F2. Suppose sun is at F2 and every planet will move around the sun in this path. This is ellipse and sun, every planet will move around the sun in this path. This is the Kepler's first law. Now suppose this planet is Earth. First I will explain what is time period of a planet. Time period means time taken by planet to complete one revolution around the sun. Time taken by planet to complete one revolution around the sun. For Earth, this time period is 1 year. As you know, Earth completes one revolution around the sun in 1 year. Now, one more important thing, average distance. No place here. I'm erasing this one. Average distance. As you can see, Earth is revolving around the sun. Now, see, at some point of time, Earth will be here, and some point of time, Earth will be here, and some point of time, Earth will be here. Now, try to think about it that this distance and this distance means distance of Earth from sun keeps varying, means here distance is minimum and as it goes away from the sun its distance will increase up to this point. This is maximum distance of planet from sun. So distance is not fixed. So how can we find the distance of a planet from sun? For this we take average data. For example, you may done the questions of average in previous classes, like 5 students in a class scored, one score 20, one score 10, one score 30, one score 15, one score 25. So if you have to take the average of this data, how you find the average? Average equals to sum of all the numbers upon total numbers, like this 30 30 30 60 plus 40 100 upon 5, so average is 20. Similarly here in this case we also take average value of the distance. Suppose we have taken 5 distance of Earth from sun at 5 different moments, one here, one here, one here, and some one here. Suppose here is 100 kilometer, here is 150, here is 200, here 300, here 150. Then we will divide these distances with a number of observation, we will get average value. In case of orbital motion, average distance of a planet is equal to length of semi major axis. This is f1, this is f2. In between f1 and f2 there will be center of the ellipse, and if you find this distance O to this point, this distance will be average distance of the planet from the sun. And what is time period? Time period is the time taken by a planet to complete one revolution around the sun. These points are clear. Now at some point in a year, earth will be at maximum distance from the sun, and at some point earth will be at minimum distance from the sun. This minimum distance is the point at which earth is at minimum distance is called perihelion, and the point at which earth is at maximum distance from the sun is called aphelion. So first law is clear. According to first law, all the planets revolve around the sun in elliptical path, and sun is situated at one of the two foci. Now we will see second law of Kepler. According to second law of Kepler, lines joining the planet to the sun sweeps over equal areas in equal interval of time. What is the meaning of this statement? Suppose here is sun and this is elliptical path of earth. So earth started its motion from here, this point, and in time period t1, suppose this is m1, in time t1 earth reaches at point m2, and if you join the trajectory of the earth to the center of the sun, the area under these lines, suppose area under these lines is a1, and at some other points, suppose this is point n1, and in time t2 earth reach point n2. Now join trajectory of earth from n1 to n2 to the center of the sun. Time taken here is t2, and area covered here is a2. Suppose this is O. Now according to this law of Kepler, if time taken by earth to reach m1 to m2 means t1 is equal to t2. If t1 is equal to t2, then area covered from reaching m1 to m2 will be equal to area covered from n1 to n2. Means if time is equal, area covered will also be equal. If time period is equal, then area covered will also be equal. That means I can write area covered is equal directly proportional to time taken. And if I have to replace this proportionality symbol with equal to sign, I have to put one constant. That means from here I can write a upon t equal to c. I will explain again. According to second law of Kepler, if uh, time taken by Earth to reach from m1 to m2 is equal uh, to reach time taken by Earth to reach n1 to n2, then area covered from reaching m1 to m2 will also be equal to area covered from reaching n1 to n2. That's it. We will solve some numerical questions on this. I'm writing formula here. A upon T equal to C. I'm writing small here. A upon T equal to C. First question is, if a planet covers 2 into 10 raised to power 4 into 10 raised to power 22 meter square area in 20 days, then find the time taken by find the find the area covered by same planet, area covered by same planet in 50 days. As I told you that area covered is proportional to time taken. More the time, more the area a planet will cover. So if in 20 days, in 20 days planet covers 4 into 10 raised to power 22 meter square area. So if we have to find the area in covered in 50 days, first we have to find area covered in 1 day. So in 1 day it will cover, if I divide this area by 20, I will get the area covered in 1 day. 4 upon 20 into 10 raised to power 22, this will be 1 by 5 into 10 raised to power 22 meter square. Now area covered, now area covered in 50 days, this will be area covered in 1 day into 50, then we will get the area covered in 50 days. 50 into 1 by 5 into 10 raised to power 22, 10 times, that is 10 into 10 raised to power 22, or we can write this as 10 raised to power 23 meter square. I will take one more question on this topic. Suppose a planet is revolving around the sun in such a way that this is planet from point, this is m1 to m2, and this is point n1 to n2. This is point O. This point is O. In the question, it is given that area covered here is A1, area covered here is A2, and time taken is T1, time taken is T2. In the question, it is given that if A1 is equal to 1.7 into 10 raised to power 20 meter square, and if T1 is 125 days, then A2 is given 6.8 into 10 raised to power 20 meter square. We have to find T2. As we know, for a planet revolving around the sun, we can write its area upon time will come equal to a constant. So if I try to find the ratio of area and time for this part, this is A1 upon T1, this will come equal to a constant. And if I try to find area covered from reaching n1 to n2 by time taken, that means A2 upon T2, the planet is same, this trajectory is same, so this will also equal to this constant C. So from equation 1 and 2 I can write A1 upon T1 equals to A2 upon T2. We have to find T2, so cross multiply here, A1 T2 equal to A2 T1. To find T2, we have to take A1 right hand side, A2 upon A1 into T1. So T2 will be A2 is 6.8 into 10 raised to power 20 upon 1.7 into 10 raised to power 20 into T1 is 125. 10 raised to power 20 to 10 raised to 20, this cancel out and this is 4. So we got this is 500 days. So if this planet is covering area 1.7 into 10 raised to power 20 meter square in 125 days, then it will cover the area 6.8 into 10 raised to power 20 meter square in 500 days. That's it. You have to just use this equation. And remember that if you increase the time period, then area covered by the planet will also increase. Now coming to third law of Kepler. Before coming to that law, now tell me, this is Sun and other planets revolving around the Sun. This is Mercury, this is Venus, and this is Earth, and further on. Average distance of Mercury, average distance between Sun and Mercury will be less than the average distance between Sun and Venus, and in these three planets, average distance between Sun and Earth will be greatest. So tell me, Which planet will take more time to complete one revolution around the sun? Obviously, Earth, because it is far away from the sun than these two planets. So, as you increase the distance between sun and the planet, uh, time taken by that planet to cover to complete one revolution around the sun will increase. That means if average distance is increased, then time period of the planet is also increased. Time period of planet also increase. But in what manner it will increase? This is given by the third law of Kepler. These are not directly proportional. They have some other relation. We will discuss that. According to third law of Kepler, square of time period of a planet orbiting the sun orbiting the sun is directly proportional to is directly proportional to cube of average distance between planet and sun. And these laws are not only valid for a planet and sun, these laws are valid for everything orbiting more heavy body, like moon is orbiting the earth, then these laws will be valid for moon which is orbiting the earth. Now, according to this law, mathematically we can write this as mathematically t square is directly proportional to r cube. We can replace this proportionality symbol with equal to sign by putting one square k r cube. Take r cube to left hand side, t square upon r cube equal to k. This k is universal constant. This k value you will get same always. uh, you can put time period of any planet, and you can put if you put time period of any planet and average distance of that planet from sun and put in this equation, you will get always same value. If you put value of time period of earth and average distance between sun and the earth, you will get some value, say k. Then if you put time period of Mars and average distance between sun and Mars, you will also get same value in that case also. That means I can write for planet 1, average distance between planet 1 and sun is say r1, and time period of that planet 1 is t1. For planet 2, average distance is r2 and time period is t2. And if you put these values in this equation, for planet 1, t1 square upon r1 cube equal to k. For this planet, t2 square upon r2 cube equal to k. From equation 1 and 2, if right hand side of both the equations is equal, then we can conclude that left hand side of both the equation will also be equal. So from equation 1 and 2, from equation 1 and 2, we can write that t1 square upon r1 cube is equal to t2 square upon r2 cube. Remember this formula, this is important one. This is all about Kepler's laws. All three laws are clear now, and I will take some problems on that third law. Then we will wind up that topic. I'm writing formula here. T1 square upon R1 cube equal to T2 square upon R2 cube. This is the formula for third law. I'm taking question. Question number 1 is two satellites orbiting the moon. Two satellites are orbiting the moon. Satellite 2 is 4 times farther than satellite 1, and if time period of satellite 2 is 16 days, satellite 2 is 16 days, find time period of satellite 1. I'm writing that as T1. We have to find time period of satellite 1. As I told you that these Kepler's laws are not only valid for sun and the planets. This is valid for any body which is orbiting any other heavy celestial body. So as we know, T1 square upon R1 cube equal to T2 square upon R2 cube. See here, satellite 2 is 4 times farther than satellite 1. Suppose this is moon and this is orbiting path of satellite 1. This is satellite 1 and this is orbiting path of satellite 2. Now tell me, if satellite 2 is taking 16 days, this is taking 16 days to complete one revolution around the moon, and satellite 1 is closer to moon than satellite 2, so it will take more days or less days. Distance between moon and satellite 1 is lesser than distance between moon and satellite 2, so obviously satellite 1 will take less days, and we have to find how many less days. Suppose this distance I am taking as r. Satellite 2 is 4 times farther than satellite 1. If this distance between satellite 1 and moon is r, and satellite 2 is 4 times farther than satellite 1, so this distance will be 4r. So I can write r1 equals to r, so r2 will be equal to 4r, and t1 we have to find, and t2 is given as 16 days. Now I'm modifying this equation. We have to find t1, then take t1 on left hand, keep t1 on left hand side and take r1 to right hand side, so it becomes t1 square equal to r1 cube upon r2 cube into t2 square. Put these values in this equation, so t1 square will be equal to r1 is r, so cube of something, I can write cube of something as 3 times like cube of r will be equal to r into r into r, and cube of 4r I can write as 4r into 4r into 4r into t2 square, 16 into 16. So r to r cancel, this r to this r, and this r to this r. We left with 4 into 4 into 4 in denominator, and in numerator we left with 16 into 16. 4 4 ja 16, 116 cancel out, and this 4. So t1 square is equal to 4. Taking square root on both the side, we will get 2. So time period of satellite 1 is 2 days. 2 days. That's it. We'll take few more questions. Uh, R1 means average distance between average distance between Sun and Jupiter. Sun and Jupiter is given as 5.2 AU. What is this AU? First, I have to explain AU. AU is astronomical unit. Astronomical unit, and it is the unit of length, like meter, kilometer, centimeter, millimeter. This is also the unit of length. Unit of length. Why we need this unit? Because if you try to find distance between Sun and the Earth, its value come around 150 million kilometer. And if you write this huge value in terms of meter, you will get a very huge number and very tricky and very difficult calculation. So making calculation easy, another unit is introduced. This is called astronomical unit, and 1 AU is equal to 150 million kilometer, and this is the distance between average distance between Sun and Earth. Astronomical unit is just the unit of length. So R1 is average distance between Sun and Jupiter, and time period of Jupiter is given as 12 years. Time period of Jupiter. Time period of Jupiter is given as 12 years. Now we have another unknown planet whose average distance from the Sun is average distance of that another planet unknown planet is R2, and this is given as 10.4 astronomical unit. We have to find time period of this unknown planet. We have to find T2. Now use this formula. We have R1, T1, R2, and we have to find T2. So we can use this formula. Take T2 this side and take R2 to the left hand side. We will get T2 square equal to R2 cube upon R1 cube into T1 square. R2 is 10.4. 10.4 into 10.4 into 10.4 upon 5.2 into 5.2 into 5.2, and T1 square. T1 is 12 into 12. Why I am not writing AU here? Because if you write AU, you have to write AU 3 times, and in denominator also 3 times. So AU to AU cancel out. So you don't need to write AU here. 2, 2, 2. T2 square equal to 2 into 2 into 2 into 12 into 12. If you try to form pair, these 2 into 2 form pair and 12 into 12 form pair, and this 2 alone. So if you take square root on both the side, 62, 1 2 will come outside and 12 will come outside, and root 2 will remain inside, and root 2 value, as we know, 1.41. If you try to 12 into 2, 24, 24 into 1.41, you will get 33.94 years. That means time period of that unknown planet is 33.94 years. It completes one revolution around the sun in 33.94 years. So on earth we complete around 34 years, and on that planet there will be only 1 year completed in that time. We can conclude from here that if we increase or decrease the distance of planet from the sun, the length of year is also changing. Like if you increase the distance, average distance of a planet, length of the year means then year will be more lengthy, like more days in year, like 500,000, 2,000 days in a year. And if we if the distance between planet and sun is reduced, then year will be shorter. Third question I am taking on that topic: if the distance between sun and earth, if the distance between sun and earth is doubled, how many days, how many days would have been in a year? If you increase the distance between earth and sun, in this case you are doubling the distance, then obviously the time taken by earth to complete one revolution around the sun will increase. So we have to find by how much amount the time period will increase. So this is sun. Initially this distance was, this is earth, present distance is 1 AU, and present time period is, this is R1, and present time period is 1 year. If you double the distance, means now this distance becomes, if currently this is 1 AU, then if you double the distance it becomes 2 AU, and we have to find T2. So from formula we can write T1 square upon R1 cube is equal to T2 square upon R2 cube. We have R1 as 1 AU, T1 as 1 year, R2 is 2 AU, and T2 we have to find. So keep T2 this side and take R2 opposite side. So T2 square equal to R2 cube upon R1 cube into T1 square. 2 into 2 into 2, and in denominator 1 into 1 into 1, that will not make any significant change to this, and T1 is 1, and this will also not make any change in our calculation I am writing. into 1 into 1 into 1. So this will be t2 square will be 2 into 2 into 2. These two 2's are forming pair. So if we take the square root, one will come outside and one will stay inside. T2 equals to 2 root 2. That means value of root 2, 1.41. This becomes 2.2 into 1.41. This is 2.82 years, and we have to find number of days. So in 1 year, one present year, as of now, 1 year equal to 365 days. 365 days. So 2.82 years equal to 2.82 into 365. So it will come around 132.22 days. 1032.22 days. That means around 1032 days. If the distance between the sun and the earth is double of present distance, then 1 year on earth will complete in 1032 days. It is almost like 3 year of present. So this topic is completed. I will attach one PDF of questions on Kepler's laws, and I will also upload one video in which I will explain how you can draw a ellipse by just using a thread and a pen. That's it for today.